Okay, moving on with our unit on probability. So in 9.2, we're going to be looking at multi-stage experiments, independent events, conditional probability, and some modeling games. So first of all, tree diagrams. If you are looking at this problem where the spinner is spun twice and the tree diagram to the right shows the possible outcomes. So with our spinner, we have it broken into 3 even sections. So there is a 1/3 probability that you would spin a blue, a 1/3 chance you would spin on red, and 1/3 on yellow. So that's what this first part of our tree diagram is showing: 1/3 blue, 1/3 red, 1/3 yellow. Okay. Now we're spinning twice. So this first part of our tree diagram represents the first spin. Now for each of those possibilities, you could have 3 potentials for the second spin. So maybe you spin blue first. The second spin could be blue, red, or yellow. Okay. Same with the red. If you spin red first, the second spin could be blue, red, or yellow. And then for yellow, the second spin could be blue, red, or yellow. So for each of those possibilities there on that second spin, there's a 1/3 each. Okay. Now, this last column represents the outcome. So if you're following this part of the tree diagram, that's showing a blue on the first spin, blue on the second spin. The next part of our tree diagram shows blue on the first spin, red on the second spin. So that's BR. And then we have blue and yellow, that's BY. Okay, and that's where all of these came from. It's just following the tree diagram. So here, if we go to red, we have red, blue, so RB. We have red, red, RR. Red, yellow, RY, and then so on for the yellow. Okay, so that's how you're going to make a tree diagram for multiple spins. Okay. So what this tells us is all of these outcomes tell us our sample space. So our sample space is blue, 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 red, blue, yellow, red, blue, red, 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 yellow, yellow, blue, yellow, red, yellow, yellow. So the probability of each outcome, since there are 9 in the sample space, the probability of each outcome would be 1/9. So that's how you would use a tree diagram for this problem to see what the probability of each outcome would be. Now, tree diagrams can get a little extensive because, if you have more, 3 branches, that was already pretty big. But if you have even more branches, then it gets a little more complicated, and maybe you don't have enough room for that on your paper, or it just gets cluttered or whatever. So another thing that you can do is make a table. Okay. In the table, you put the column as your first possibility, so blue, yellow, red. The row is your second, blue, yellow, red. It really doesn't matter which is which, but you look at all the possibilities here. So B with B, B with Y, B with R, and then go down to the next row, Y with B, Y with Y, Y with R, and so on. Once again, you can see there are 9 possibilities in that sample space. And so what's the probability that you would spin a blue and then a yellow? Well, there's only 1 blue and yellow possibility, so it would be 1/9. Okay. Now, once again, the table's probably a little more organized and doesn't take up quite as much space, but if you have, more than 3 or 4 possibilities on each one, it can still get a little complicated. So we also have this little formula here, this theorem, that talks about a multiplication rule for probabilities for tree diagrams. So for all multi-stage experiments, the probability of the outcome along any path of a tree diagram is equal to the product of the probabilities along the path. So for our spinner problem, the probability of each outcome, well, for the first spin, the probability whether you're choosing blue, yellow, or red, it's 1/3. For the second spin, it's 1/3. So if you multiply those together, you get 1/9. So a little easier, right? You could do that in, just in your calculator or in your head, and you don't have to go through and make a table and make a tree diagram. Now, some of you are more visual learners, so you may like the table or the tree diagram better. That's fine. You choose whatever is easier for you, but that's 3 different ways that you could solve that spinner problem. Okay, try this using the spinner from the previous problem as well as a die. What is the probability of spinning a red and then rolling a 3? So you can solve this any of the 3 ways you would like. Pause the video and see if you get the correct answer. Okay, so I solved this using our multiplication theorem that we talked about back here. You all know me. I want to get the answer as quickly as possible. So when you are spinning using that same spinner with our 3 options, I would have a 1 in 3 chance of getting a red. If we're rolling a die, then there's dice have 1 through 6 on them. So die is the singular for dice. I know it feels weird to me too. But anyway, rolling a 3, there's only 1 possibility there. So there's 6 options, so that's a 1/6. So to get my probability of spinning a red and rolling a 3, I'm going to take 1/3 times 1/6, which gives me 1/18. Okay, next example. When rolling a pair of fair dice, find the probability of the event A, which is rolling double 6s. Okay. So if you are looking at a table for this, you've got 1 through 6 on the first row, or on the first die through 6. Here are all the possibilities that you could get. And if you look here, that's 36 possibilities. So if you want to roll double 6s, the only double 6 you see is right here. Okay. So that's going to be 1 out of 36. Okay. Now you could also do this with our multiplication rule that we just talked about. In order to get a 6 first, there's a 1 out of 6 chance. In order to get a 6 second, on the second die, that's a 1 out of 6 as well. So 1/6 times 1/6 would still give you 1 over 36. So the probability of A is 1 over 36. On B, find the probability of rolling a sum of 7 or 11 when rolling a pair of fair dice. So we saw earlier, there's a possibility of 6 different rolls. Okay. Now, if I go through here on each of these and figure out my sums, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, so on. I could make another table to show the sums, and this is what it would look like. There's my 1 plus 1 was 2, the 2 plus 1 is 3, and so on. Well, when I look here, there are 6 ways to form a 7. So if you look right here, we have all of these are 7s. Okay. So since there's 6 different ways to form a 7, that gives me 6 out of 36 for that probability. Then when I look to see how many ways could we form a sum of 11, we only have 2 ways there. I've circled those in green. So that's 2 out of 36. So it's 6 out of 36 for the sum of 7 and 2 out of 36 for the sum of 11. So this time, since we're talking about sums, my sample space for the experiment is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So all that is the numbers that I have here. It's 2 through 12. However, our sample space isn't uniform, so that just means that the probability of each of the given sums are not equal. We saw that back here with 7, we had a probability of 6 out of 36. With 11, it was 2 out of 36. Okay. So if we want to find the probability for each of those outcomes, okay, the outcome of 2 or the sum of 2, there was only 1 out of 36 for that, because look back here at our table, that's the only 2. Okay. In order to get a 3, there were 2 possibilities there, so that probability is 2 out of 36. For 4, it's 3 out of 36, and so on. Okay. So all of these out of 36s just represent how many sums of the above number you have. So for 9, when I look back here, there's 1, 2, 3, 4, 9. So that would be 4, 9 over 9. We already figured out the 11 was 2 out of 36 and the 7 was 6 out of 36. So that's where that came from. So the probability of rolling a sum or 11 is just taking our 2 probabilities, 6 out of 36 and 2 out of 36, and adding those together. Okay. So was all of this necessary for this part? No, we already found those, the 6 out of 36 and the 2 out of 36. We found those back here, right there, and right there. So you're just going to add those together to get your probability. And then you may be wondering, why didn't we reduce before? Okay, well, that wasn't, those weren't our final answers. So we're going to reduce on our final answer here. I didn't reduce before because I wanted to make sure I would have the same denominator, and I do if I leave them here as 36. Now I have to just add the numbers in the top. 6 plus 2 is 8. 8 over 36 reduces to 2/9. Okay, in this example, a fair pair of dice is rolled. Let E be the event of the rolling a sum that is an even number. F is the event of rolling a sum that is a prime number. Find the probability of rolling a sum that is even or prime. Okay, and so this is our notation for basically our question. Find the probability of rolling a sum that is even or prime. So the P stands for our probability. Our events are E and F. And this little U symbol is our union symbol, and it's standing for or. Okay. So if we're rolling a pair of dice and we want to see if the sum is going to be an even number, okay, well, we just saw in the last example, this is our sample space, 2, 4, 6, 8, 10, 12, 3, 5, 7, and 11, okay? So if we're rolling our dice and we're looking at the sum, in order for it to be even, we saw in our table earlier that our sums went up to 12. And then if it's going to be odd, that would give us 3 to 11 because we did not have 1 as a sum. Okay. So taking our chart we came up with earlier. So that's one reason they went ahead and we calculated all of those in that table. We didn't need it for that last problem, but they were going to use it again in this problem. So this is just going to save a little bit of time there. So when we're looking at the probability of even or the sum being even or odd, what I'm going to do is take the probability of each of those in that we have listed here. So the probability of 2 plus the probability of 4 plus the probability of 6 plus the probability of 8 plus the probability of 10 plus the probability of 12. Those are even sums. Then I'm going to add in all the odd sums, probability of 3, 5, 7, and 11. Okay, so that's 1 over 36, 3 over 36, so on. And I'm just grabbing the numbers from the chart for each of these. So 2 is here, 1 over 36. 4 is 3 over 36 here. 6 is 5 over 36, and so on. Okay. So then we're going to add all of those up. They all have a denominator of 36, so we just need to add 1 plus 3 plus 5 plus 5 plus 3 plus 1 plus 2 plus 4 plus 6 plus 2, which gives me 32 over 36, and that reduces to 8/9. Now, here's another option, because as you can see, that was pretty complicated. That was a lot of fractions to add up. Thankfully, they all had the same denominator, but still it was a lot. So another thing that you can do is when you look at our E sample space and our F sample space here, we can see that they are not mutually exclusive. So what that means is they have a common number. Okay, see how we have two? I think I said odds on these, but that one was prime, wasn't it? Got mixed up there. F was prime. Okay, I just got to rolling on even and odd, but it was even and prime for our sample spaces there. Okay, so when I look here, I have that number that repeats. Okay, so I'm not really going to count it twice. So what I can do is figure out the probability of E and the probability of F, and then subtract off the two. So that might be easier for you. Okay, so that would be 18 over 36 and add 15 over 36 and then subtract off what they had in common, the 1 over 36. Okay, so that's another option. There's not quite as many fractions there to add. Sometimes that's helpful. Okay. Okay, another option for solving that same problem would be to look at our sample space for E and our sample space for F. So when I put E and F together, here's what I have. So between, and actually that should also include a 12. I'm going to go back and fix that so it'll be fixed on your PowerPoint. So when you put these together, the only number that's missing is 9. Okay. And so what you can do is this little bar here means the complement. So it means like what is missing. So when I look at this part, the probability of the 9 from back here is 4 out of 36. So if I'm including everything except for this, okay, everything is 1. So if I subtract 4 out of 36 from that, that'll give me everything but that. So 1 minus 4 out of 36 will be 32 out of 36, which reduces to 8/9. So it's another option. Okay. And so keep in mind this little bar, remember that means complement. So that means basically what's missing. Okay, here's another multi-stage experiment. This time we're starting out with figure A. This is a box and it has 3 balls in it. One of the balls is colored and the other 2 are white. So if a ball is drawn at random and the color is recorded, then you can make a tree diagram for the experiment. So I would have a 1 in 3 chance of drawing the first white ball. I would have a 1 in 3 chance of drawing the second white ball and a 1 in 3 chance of drawing the colored ball. Okay. Because each ball has the same chance of being drawn, okay, we have the 1 over 3, 1 over 3, 1 over 3. But these two are the same type of ball. So I could combine that and make a tree diagram that's not quite as complicated by just drawing 1 white ball and 1 colored ball. Okay, so the white ball, putting those 2 together gives me 2/3, and then I have 1/3 here. So suppose a ball is drawn at random from the box in the figure and its color is recorded. The ball is then replaced and a second ball is drawn and its color is recorded. So your sample space for this 2-stage experiment might be recorded using the ordered pairs. Okay, a colored ball with a colored ball with white, white with colored, white with white. Those are all the potential types of draws that we could have there. Okay, you could show the tree diagram for the experiment by taking what we had in part C back here for our first draw, the 1/3 for the colored ball and 2/3 for the white ball, starting out with that for the first draw, and then basically you repeat this for each of those for the second draw. So let's say for the colored ball, if you're doing bouncing off of that for the second draw, you've got a 1/3 chance of drawing a colored ball again and a 2/3 for a white ball. And same thing here. If you draw a white ball first, your second draw, you could have 1/3 and 2/3 possibilities here. So here are those outcomes that we listed as ordered pairs in our sample space before. Okay. And you can look on your tree diagram to figure out what to multiply together. So 1/3 and 1/3 is 1/9. 1/3 and 2/3 would give me 2/9. 2/3 and 1/3 is 2/9. 2/3 and 2/3 is 4/9. So the probability of drawing two colored balls is 1/9. A colored then a white is 2/9. A white then a colored is 2/9. And then white is 4/9. Okay, for all multi-stage experiments, the probability of the outcome along any path of a tree diagram is equal to the product of all the probabilities along the path. So that's what we ended up with here, was we multiplied the numbers along the path of our tree. Okay, so this time, let's see what happens without replacement. So this time we draw two balls, one by one, but you don't replace after the first ball, okay? So the first draw, you have a 1/3 chance of getting a colored ball, a 2/3 chance of getting a white ball. But remember, you say you draw the colored ball first, you're not putting it back in, so there's no chance you'll draw another colored ball because there was only one in the box to start with. You will draw a white ball next, and that's 2 out of 2. That's why that gives us 1. Now, for the white ball, you could draw a colored ball next, which is a 1 out of 2 chance, but you could also draw a white ball again, so 1 out of 2 chance. So that second draw, this time, there's only 2 balls left, and so that's why our denominator is a 2. There's only 2 in our sample space this time. Okay, so these are the possible outcomes. If I follow this tree diagram, I have colored ball, and if I multiply along my path there, I have 1/3 times 0 over 2, so there's a 0 probability that this will happen, which makes sense if you think about it. You're not replacing the first ball you drew, so there's no way you would get another colored ball in the second draw. For the colored ball and then white, you're going to multiply 1/3 times 2 over 2, which gives me 2 over 6, or 1/3. And then here for white colored, you're going to multiply 2/3 times 1/2 to get 1/3. And then white, you're going to do 2/3 times 1/2, which is 1/3. Okay, independent events. When the outcome of one event has no influence on the outcome of a second event. That's called an independent event. So if 2 coins are flipped and event 1, we'll call it E1, is obtaining a head on the first coin, and event 2, which we'll call E2, is obtaining a tail on the second coin, then E1 and E2 are independent events because one event has no influence on the possible outcomes. So here's a tree diagram of what that would look like. You have a 1 out of 2 chance of flipping a head, a 1 out of 2 chance for a tail. Same thing on your second flip, 1 out of 2 for each. Okay, so you could have a heads, or a head tails, or a tails head, or a tail. Okay, and then you're just going to multiply along that path. 1/2 times 1/2 means I have a probability of 1 over 4 of flipping the heads, then another head. For head tail, 1 out of 4. For tail head, 1 out of 4, tail, tail, 1 out of 4. Okay. So this is our notation for any independent events, E1 and E2. The probability of E1 and E2 is going to be found by multiplying by the probability of each. Okay. So for that particular problem, if I didn't want to have to draw out a tree diagram, and I just wanted to know the probability of obtaining a heads and then a tail, well, you have a 1 out of 2 chance for heads and a 1 out of 2 chance for the tail, so 1/2 times a half is a fourth. And that's basically what it's telling you to do, 1/2 times a half. Okay. Okay, this next example, the figure shows a box with 11 letters. Some letters are repeated. Suppose 4 letters are drawn at random from the box, one by one, without replacement. Okay. So that's a keyword is important. What is the probability of the outcome baby with the letters chosen in exactly the order given? Okay. So first of all, note we have 11 letters. Okay. We want to know only about the tree branch that would lead to B-A-B-Y. Okay. Well, if I look here at my letters, how many B's do I have? 2, right? So I have a 2 out of 11 chance of drawing a B. When I look at my letters here, how many A's do I have? Just 1. But remember, we didn't replace the first letter. So now I only have 10 letters in the box. So that's why this is 1 out of 10. Okay. To draw another B, we've already drawn a B over here, so I only have 1 left. Now there's only 9 letters in the box, so 1 out of 9. And then for the Y, in the word probability, there's only the 1 Y, and we are down to 8 letters in the box, so it's 1 out of 8. Okay, and that's what all that's explaining. And so now I just take these numbers and multiply them together. 2 out of 11 times 1 out of 10 times 1 out of 9 times 1, 8. That's going to give me 2 over 7,920, which I will reduce. There's another typo. So I will fix that, but that's going to be 1 over, and then 7,920 divided by 2. So it should end up being 1 over 3,960. Let me see if this will let me write on that. Pen 1, oh, look at this, over 3,960. Please excuse this, I'm writing with my mouse, but at least we have the right answer on there now. Okay. Okay, moving on to the next one. This time we have 3 boxes shown below. We're going to take a letter from the first box and randomly draw it, place it in the second box. Then we'll randomly draw a letter from the second box and put it in the third box. Finally, a letter is drawn from box 3. What's the probability that the letter from box 3 is a B? Okay, so here's what our tree diagram looks like. So our first draw, we had 2 A's and 1 B. So that's a 2/3 chance of drawing an A and a 1/3 chance of drawing a B. Okay. Then in the second draw, if we drew an A, then we already had an A. Now we have 2 A's and a B. So it's 2/3 for another A and 1/3 for another B. If we happen to draw the B in the first box and put it in the second box, now we have 2 B's and 1 A. So that would be a 1/3 chance of drawing an A and a 2/3 chance of drawing a B. In the third draw, okay, we have 4 letters here. Okay, if we draw a letter from box 2 and put it in box 3, we now have 5 letters. Okay, if we were to draw an A, we would have 2 A's out of 5 and 3 B's out of 5. Okay, if we were to have drawn a B in the second box to put in the third box, we would only have 1 out of 5 chance of having an A, because this would be our only A, but then there would be a 4 out of 5 chance of B's. Okay, same idea here. If we put the A in the third box, we'd have 2 A's out of 5, and then we would have 3 B's still. If we were to put a B in the third box, we'd only have 1 B out of 5, and 1 A out of 5, and then 4 B's total. Okay, so to figure out our outcome, like to figure out if we would actually draw an A, then I would multiply 2/3 times 2/3 times 2/5. Okay. To figure out if I would draw AAB, then I follow this path: 2/3, 2/3, and 3/5, and so on. Okay. So if I want to know the probability that I draw a B from box 3, see the blue ones? Those are the outcomes that show a B in box 3. So basically I take those 3 outcomes and I'm going to add them together. So 12 out of 45 here, 8 out of 45, 3 out of 45, and 8 out of 45. When you add those all together, you get 31 over 45. Okay, then for conditional probabilities, if A and B are events in sample space S, and the probability of A is not 0, then the conditional probability that an event occurs given the event A has occurred is given by this formula. So here's how this looks. What is the probability of rolling a 6 on a fair die if you know that the roll is an even number? Well, the probability of rolling a 6 is 1 out of 6. The probability of rolling an even number is a half. So this formula tells me to take 1/6 and divide it by half. 1/6 divided by 1/2 is 1/3. Okay, here's a try problem for you. So pause the video and see if you can answer questions A through E about this bag of chocolates. When you think you have your answers, come back and we'll look at these together. Okay, so here is what your tree diagram would look like with replacement and without replacement. Okay, so your options were white, milk, and dark, and we had a total, when I add up 2, 5, that gives me 7 plus 3 is 10. So there's 10 pieces of chocolates here. Okay, so that's why these probabilities are out of 10. There were 2 whites, so that's 2/10. There are 5 milks, so that's 5 out of 10. And there were 3 darks, that's 3 out of 10. Okay, okay, you're replacing, so in the second draw, these are still all out of 10. Now, for the other tree diagram, you're not replacing. So you start out the same, 2 out of 10, 5 out of 10, 3 out of 10. But the second draw, they're all out of 9 because there are, you didn't put the first piece of chocolate you drew back in. So there's only 9 pieces left. So if you drew a white the first time, then there's no longer 2 whites, there's only 1. So that's where the 1/9 came from. Okay, there's still 5 milks, still 3 darks. If you drew a milk for the first time, then the milk is the one that changes 4. There's only 4 now instead of 5, so on. If you drew a dark for the first time, then there's no longer 3, there's 2. Okay, so that's what that one's about. And then the second part, what's the probability that she picks 1 white chocolate and 1 dark chocolate with replacement? So you take 2/10 times 3/10 and get 6/100, which reduces to 3/50. On C, that one's talking about without replacement. What's the probability she picks 1 chocolate and 1 dark? So, or 1 white chocolate. So there's the white chocolate 2/10, and the dark is 3/9. Multiply those together to get 6/90, which reduces to 1/15. And then for D, what's the probability with replacement that her second pick is milk chocolate, given the first pick was milk chocolate? We're doing with replacement. So if the first pick is milk chocolate, the second pick would be milk chocolate. That would be 5 out of 10, which reduces to 1/2. And then without replacement means I'm going to use that second tree diagram. Her second pick is milk chocolate, given the first is milk chocolate. So milk chocolate, that's going to be 4/9. Okay. Okay, notice we didn't reduce the fractions in the tree diagram. We waited and reduced it in our final answer. And that's just because sometimes it's easier to multiply out or add the fractions depending on what type of probability it's asking us to do when you have the same denominator. So a lot of times it just works out easier to reduce as you go, or to reduce at the end, but you decide what's easier for you. Yes, you can use your calculator on this stuff. If you need help with using the fraction button, let me know. But I'd like for you to try, since we spent so much time in 205 working with fractions and how to reduce them, multiplying, adding, and subtracting, try to do a lot of it without it. That way you'll still keep those skills up, because you're going to need them for your students. You won't let them be able to let them use the calculator on everything. Okay, reach out if you have any questions, and don't forget about the discussion board for this week.